Hello everyone, this is Doug, and in this video I'm going to tell you how to assign oxidation states on organic molecules. And really this works for inorganic things too, but we're going to focus on organic molecules. What you want to recall is that oxidation states, they basically just describe what the charge would be, like what the formal charge would be on any given atom if all of the bonds broke, right? So it's kind of all about like who owns the electrons, and it's just based on electronegativity. So I have my little periodic table over here. I just want to remind you real quick. Right, we don't count the noble gases. The most electronegative element is over here, fluorine, and then we have cesium and francium are the least, right? So this is the most electronegative, the least electronegative elements. And so what do I mean by if all the bonds broke? Like let me show you here. So we've got water as our first example here. So let's look at good old H2O. So H2O. What we're saying here is that you look at each bond and you break them and you decide who's going to get the electrons, which again is just based on electronegativity. So if I'm talking about this bond, the HO bond on the left here, I want to know which one is more electronegative. And if I look at oxygen and I find oxygen on the periodic table, so let me go find oxygens over here next to fluorine. And hydrogen, technically, right, I'm sure you remember, hydrogen's over here, but in terms of electronegativity, we need to bring it over here next to boron and carbon. So here's my boron, here's carbon. But regardless, the idea is that oxygen is more electronegative than hydrogen. So what that means is that if you broke this bond, oxygen would get those 2 electrons. And same thing for the OH bond on the right-hand side. Oxygen's more electronegative than hydrogen, so if that bond broke, oxygen would get those electrons. And again, it's just because oxygen's more electronegative than hydrogen. And so what that means then is what I'd end up with is a hydrogen that has no electrons because those 2 electrons went to oxygen. This oxygen gained those 2 electrons. I'll try to make them a little more bold, right? It gained those 2 electrons. Those are the ones that were in the OH bond. And it has its lone pair still. And also that oxygen gained the 2 electrons that were in the other OH bond. And again, you have an H that has nothing. And then you just do your formal charges, right? Your number of valence electrons minus the dots and sticks to figure out what the charges would be. And so if I look at the hydrogen on the left here, this one has a valence, right? It has a 1 valence electron minus the number of dots and sticks. It has no dots and sticks around it, so its formal charge is just +1. If I take a look at the oxygen in the middle, its number of valence electrons is 6, number of dots around it is 8, so that is a -2. So I'm going to give the oxygen a -2 charge, and then I'm going to go over and look at this hydrogen. It's the same thing. It has 1 valence electron minus the number of dots and sticks around it equals a +1, so that's also +1. So that means these are all of the formal charges. We'd say the formal charge on hydrogen is +1. The formal charge on here, let me erase that. I don't want you to think this is like an ion. Right, the formal charge on hydrogen is +1. The formal charge on the oxygen is a -2, and the oxidation state of the other hydrogen is a +1, right? So those would be the oxidation states: a +1, -2, and a +1 for water. If you're lucky, if you're going to assign them for water, that's what they would be. And I'll write this up here. I know I just kind of spoke through this, but you've done this before. Just remember that to figure out the formal charge, right, that was just the number of valence electrons minus the added up number of dots and sticks around your thing, right? Or you could say all of the non-bonding and half the bonding, same thing. So if I take a look at hydrogen peroxide, so now I've got HOOH. I would do the same sort of thing here, right? If I look at this OH bond, again, oxygen's more electronegative than hydrogen, so it takes those electrons. But now I have an OO bond. And since I have an OO bond, right, one of those oxygens is not more electronegative than the other one. So they don't split heterolytically, they split homolytically. So we're saying if we break this, 1 electron is going to go to 1 oxygen and 1 electron is going to go to the other one. right? So if you look at like this electron's still going to stick with the left O, this electron's still going to stick with the right O, and it's not that two are going to go one way or the other because, again, they have the same electronegativity. Now with this OH on the right-hand side, again, I'll say that the electrons go to the O because O is more electronegative than hydrogen, which gives us a hydrogen with nothing. So I've got a hydrogen with no electrons around it. I've got this oxygen that had its lone pairs, and now it gained those 2 electrons from the OH bond, and over here I'm throwing 1 electron that it stole from the OO bond. Now, my other oxygen also has 1 electron that it stole from its OO bond. It still has its lone pair, and now it has the 2 electrons that it took from the H, because it's more electronegative than the H. And you'll find, if you go through this, the same sort of thing, right? This H, again, is 1 minus 0, so it has a +1 oxidation state. And it, if I look at the second oxygen, it had, again, 6 valence electrons minus, now in this case I have 1, 2, 3, 4, 5, 6, 7 electrons around it, so its oxidation state now is only a -1. If I look at the next oxygen here, same story, 6 minus 7 is -1, so its oxidation state is also -1. And then lastly, this hydrogen over here, 1 minus 0, is also +1, so it has a +1 oxidation state. +1. So oxygen, right, in the water molecule had a -2 oxidation state. That meant that it was more reduced. And the oxygen and the hydrogen peroxide only had a -1 oxidation state, which means it's a little more oxidized, which hopefully makes a little sense. We've done some reactions with hydrogen peroxide and we've used it as an oxidizing agent where it turns into water. But yeah, hydrogen peroxide, right, those oxygens are slightly more oxidized than they are in water. And you can figure that out just by comparing the electronegativities of things. Also in Gen Chem, you may have memorized some rule about if you have an OO bond, and oxygen's -1 in that case, but it's -2 in all other cases, which is not totally true, but this is kind of reinforcing that idea. So again, the oxidation state is what the formal charge would be if those bonds broke. Now, obviously, in the real molecules, all the bonds don't break, but this is just a way for us to keep track of kind of, you know, to whom do the electrons belong? Like, where are the electrons really? Where's more of their electron density? Can we oxidize or reduce atoms any further is the idea. Let's take a look at some more examples. So same thing, only now I have some organic molecules, right? I threw carbon in here since this is OChem. And I'm going to do the same thing. So first I have dichloromethane here, which is a solvent that we've used. So this is a carbon with 2 hydrogens on it and 2 chlorines. And over here I have methanol. Draw methanol out. Right, these are the only ways I could possibly put these molecules together, so I just drew them out for us. It's the same thing for the organic molecules as we did for the water and the hydrogen peroxide. You just go through these and you ask which one is more electronegative. And so I'll go ahead and I'll remind us, right, that hydrogen really belongs right here. This is boron and carbon, nitrogen, oxygen, fluorine. Chlorine's right below fluorine. That'll be helpful. And I think that's all the atoms that I have represented here, yeah. And then we, again, our electronegativity trend up and to the right. So I go and I look at a CH bond. I see that carbon is more electronegative than hydrogen. Barely, but it is more. So I'm going to have those 2 electrons go to the carbon. So, boom. Same thing for this CH bond. Those 2 are going to go to the carbon. But now my carbon-chlorine bonds, right? Chlorine is more electronegative than carbon. So that means they're going to get those electrons from carbon, and those are going to get electrons from carbon. Which means now if I look at this afterwards, I'm going to have an H with nothing, an H with nothing, a carbon that has the electrons from those bonds, right, because it took electrons from those. And then I'm going to have chlorines that have 8 electrons around them. Which means I can now assign my oxidation states, right? I can say that the oxidation state for the hydrogens was +1 because they lost that electron, basically. They're a 1 valence electron. Or in other words, right, 1 minus 0 is +1. The carbon looks kind of funny the way I drew it, but the point with the carbon here, it's the same point as on the previous slide. Carbon normally has 4 valence electrons. In this case, I have 4 electrons around it, so its oxidation state is going to be 0. So this carbon's actually has an oxidation state of 0. Now, the chlorines, different story here. So they are supposed to have 7 valence electrons around them, but they have 8 dots around them, so they're -1s. And both of these are the same, so I'll just replicate that. And that would be all the oxidation states of the atoms in dichloromethane. You'll notice that carbon has 2 elements on it that are less electronegative than it, and 2 that are more electronegative than it, which is why it's actually an oxidation state of 0 right now. This is going to look slightly different for my methanol example. Again, we said that CHs, the way I'm going to deal with CH is the carbon's more electronegative, so the carbon gets those electrons, gets those electrons, gets those electrons, but in the O-C bond, carbon gets those electrons, and I have an OH bond too, I might as well do that one too. I'll break that also. So again, if all of the bonds broke, I'd have an H with nothing. Whoops. Erase this. I'd have an H with nothing, a carbon here, an H here with nothing, an H here with nothing. This carbon got these 2 electrons, and these 2 electrons, and these 2 electrons. The oxygen got those 2. It had its lone pair, and it took electrons from that hydrogen, and then the H was out there. So again, hydrogen is going to be +1. Hydrogen is pretty much always going to be +1 unless it is connected to its, well, that's not necessarily true. If you had a hydrogen with like sodium, for example, since sodium's less electronegative, then hydrogen would be -1. Or if you had H2, then hydrogen would be 0 because it would get the 1 electron if it broke its bond homolytically, but regardless. Now, in this case, my oxygen here, I'm going to draw a little arrow to it, right? Again, the valence electrons is supposed to have 4, but now I have 6 electrons around it, so its formal charge is -2 here. And then my oxygen should have 6, not 7. Should have 6, but there are 8 things around it, so its formal charge would be -2. So the oxygen has a -2 charge here. What I want to point out here is that now I can see a little bit more easily, I think, which carbon is more oxidized. Or in other words, which one has a higher oxidation state, right? So if I take a look at these 2 carbons here, right? I'm comparing this carbon versus this carbon. I see that the oxidation state of this carbon is 0 in the dichloromethane, but in the other one, it's -2. And these oxidation states, they're the same oxidation states as what you did in Gen Chem. The larger the number, the more positive the number, the more oxidized you get. The lower number, the more reduced you are. So apparently in dichloromethane, this is more oxidized than in methanol, because methanol is a -2. That's a lower number than 0, right? You'd rather have $0 than -2 probably. So we can actually start to compare what atoms are more oxidized than other ones. The hydrogens have the same oxidation state, and both of these molecules are both +1, so nothing's really different about those. And then all the other atoms are different, right? The chlorines and the oxygens are different here. So we can do this for really any atom, for any molecule or compound at all. You just look at the electronegativities and you assign the formal charge for those, and that's actually the oxidation state. So I'm going to give you a shortcut to what we've been doing. I've been blowing these up, but here's kind of the short. Again, you can assign oxidation states for any atom in any molecule. So sometimes we just like focus on like the one that we're interested in, but this works for all atoms. So again, let me draw out my dichloromethane. I'll draw out methanol. What I'm saying here is that what we basically are doing is that we ended up assigning a +1 for each attachment to a more electronegative atom, and a -1 for each that had a less electronegative atom, and a 0 for each identical atom. So, like, let's say I'm going to look at this carbon here, right? What I'm saying is that if I want to know the oxidation state of that carbon, what I can do is I can just assign the things that are attached to it, right? So the hydrogens are less electronegative than carbon is. So I can assign, like, I can say minus, okay, that's worth -1, that's worth -1. And since the chlorines are more electronegative than carbon, I can say, well, I'm going to assign that as a +1 and a +1. And then I add these all together, right? So I have a -1, a -1, a +1, and a +1. That all adds up to 0. So that carbon's oxidation state must be 0. That's the oxidation state of that carbon, which is what I said on the previous slide. You can go back a few seconds and take a look at that. But we said that the oxidation state of that carbon was 0, and this agrees with that. I could have, hypothetically, let's just do this real quick. Let's say I wanted to know, for some reason, I wanted to know instead the oxidation state of the chlorine, right? Let's say I was like, I don't really care about the carbon. I want to know what's the oxidation state of the chlorine. You do the same rules. You then look at the things that are attached to chlorine. In this case, only the carbon is attached to chlorine. And carbon is less electronegative than chlorine is. So you assign a -1 to the chlorine. So now the chlorine is just -1. That's the only thing that's attached to it. So that must be the oxidation state of chlorine is a -1. Let me erase that cruddier one. You can do this for any given atom. Sorry if that was confusing. You can ignore that for a second, but let me do the next one. So again, I'm going to look at carbon just so I can compare these. So here's my carbon. I'm going to start assigning values to everything that's attached to so that I can start figuring out what the oxidation state is. Again, the hydrogens are all going to be -1 because they're less electronegative than carbon, and I'm going to give a +1 to the oxygen because it's more electronegative. So again, I have -1, -1, -1, +1. That all adds up to a -2. So now I know the oxidation state of this carbon is -2, just like I knew that the oxidation state of this carbon was 0. And that's just because I'm looking at what is it attached to. Let me do a different, well, no, I'll do that on the next page. Let's look at methane. You're probably ahead of me on this one, and I'll do carbon dioxide also over here. If you take a look at methane, right? So say I want to know about this carbon here. Let me go back. Say I want to look at this carbon here. I would do the same thing. You just assign values for everything that's attached to. All of these are hydrogen. All of them are less electronegative than carbon. So just -1, -1, -1. So that would be -1, -1, -1, -1. So, or in other words, -4. So this carbon in methane apparently is -4. Just adding those values up. And you are probably way ahead of me on this. But the carbon here in carbon dioxide. Now what we're going to do here, this is a good example to do. I have a carbon that's really attached to 2 oxygens, but it's attached to each of them twice. So we're going to count one of the bonds as a -1 and the second one as another -1. And then I go to the other oxygen. Since it's double bonded, I'm going to assign a -1 for each one of those, right? So if you do have double bonds or triple bonds to something, you just keep on adding up these numbers, right? So a triple bond to an N might be like a -3 because it's an attachment to an N and an N and an N. So you're going to multiply them up if you see multiples, and we'll see examples of that in a second. So that means that this carbon right here, oops, sorry, not minus, these are all pluses, right? Because oxygen's more electronegative, so they're a +1 for each of them. That means this carbon is a +4 value. So I was able to figure out these carbons, the oxidation state of these carbons, and I can ask questions like, well, which is the most reduced carbon, or which is the most oxidized carbon? And again, the higher the number, the more oxidized it is. So I can say things like, oh, hey, look, carbon dioxide is the most oxidized because it has the highest number, +4. So most oxidized. Which also makes sense. It has the most oxygens on it, which is where these terms come from. But yeah, it has the highest number. And then the most reduced one, you're just looking for the lowest number, which would be methane. This is the most reduced one. So I'll put most reduced. And then my second most reduced would be methanol, the middle. Then the next one would be, so this would be the lowest one. Dichloromethane's right in the middle. But you can just arrange these. And again, I just looked at carbons. I could have done this with any atom. It doesn't have to be carbon atoms. So here's a bunch of examples, right? I'll do another video on identifying oxidation versus reduction, but just to give you an idea of how this can be applied to reactions if you want to figure out if something's oxidized or reduced. What I'm going to do here is I'm going to be focusing on the atoms that are really changing here. So like in this example, it looks to me like the carbon is changing, right? I had a ketone, now I have an alcohol. So I'm just going to go and I'm going to assign the things that the carbon's attached to, right? I see that this is clearly a carbon, that's a carbon, and I have two O's. So since I have a carbon-carbon bond right here, I'm going to give that a 0 since it's the same atom. Here's a carbon-carbon. I'm going to give that a 0. It's the same atom. Because remember, those split the electrons. They don't go one way or the other. And then I have a double bond O, so that means that oxygen is more electronegative. So I'm going to give it a +1 for each of the bonds to O. So overall, this carbon right here has a +2 oxidation state. Right? That's what I'm figuring out. It's got a +2 oxidation state. If I go over to this molecule on the right-hand side, the alcohol, the isopropanol, I see again that it's attached to a carbon. This carbon's attached to a carbon, there is an H here, and then it's attached to that O up there. So I'm going to give, again, the carbons are worth 0 because it's the same element as the thing that I'm asking about. Oxygen, again, is going to be +1, but now there's only one bond to it. And then hydrogen is going to be -1 because it's less electronegative. So if I take that all together, now I see that my carbon comes out to be 0. Now its oxidation state is 0, right? Because you have a 0, 0, a +1, and a -1. Now it says 0. So it looks like to me that this must have been an oxidation or a reduction, right? If I go from +2 to 0, I've reduced the oxidation state, or in other words, we must have gained electrons, so this must have been a reduction. Right, and you probably remember these rules from Gen Chem. It's the same thing. This is a general chemical principle, right? Oxidation is loss of electrons, reduction is gain of electrons. Let's do the next example here, and then I'll give you time to do the other ones here. But same story. Let's say we take the same ketone, acetone. I'm going to look at the same carbon, ask myself what's going on with that carbon. Say it's the same molecule, so I'll just go through this quickly, right? That's a carbon, so 0 and a 0, and a +1 and a +1, so that sucker was a +2. It's the same molecule, it's the same thing. But now if I look at this carbon over here that I highlighted, it's attached to a carbon and a carbon, so those are both 0s, and it's attached to an oxygen on the right, which is worth a +1. And it's attached to the oxygen on the left, which is also worth a +1. So if I add that all up, this is still a +2, which means that, right, if I look at this, I go from +2 to +2, this is not a redox reaction. Right, it's not a redox reaction. You didn't change the oxidation state. You changed the molecule, it certainly looks different, but this must have been something else. It's not a reduction and not an oxidation. So I would take a minute. Why don't you just pause right here, take a minute to do the last two. For this one here, both of these are changing, so why don't you see what's going on with both of these suckers? And for the one over here, the nitrogen's really where things are changing. So take a look at those. So pause right here, see if you can do those, figure out if they're oxidations or reductions. So hopefully you actually gave these a try. I'm going to go ahead and fill in the hydrogens that are attached here just because I want to do this for the record keeping. Same thing here. And I'm going to go ahead and assign the charges for each of these carbons. So my carbon on the left, the secondary carbon, it has a carbon right here, so I'm going to give that a 0. It has two, right, this double bond C, I'm going to count that as 2 zeros for it, since it's like 2 bonds to a thing. Remember, we multiply those up. And then the hydrogen, again, is less electronegative, so I'm going to give it a 1, a -1. So that means this carbon over here on the left has a -1 oxidation state. Now this is going to get kind of messy. I'll try to do this in red. But let's say, I'm going to erase this stuff. La-di-da-di. Oh, I erased a lot of things. That's okay. I'm going to highlight this one in red just so we can kind of look at it differently. For the carbon on the right-hand side, again, it's attached to a carbon right here, which we're going to count as 0 and 0. And it has 2 hydrogens on it, so I'm going to give -1, -1. That means the carbon on the right-hand side had a -2 oxidation state. Now I'm going to go look at the right-hand side and see what I can see here. So this left-hand carbon right here is attached to a carbon and a carbon. Both of those are worth 0, but now it has 2 hydrogens on it, -1, -1. So it went to a -2. So it looked like the carbon on the left was actually reduced, right? It went from -1 to -2. Let's see if this also had the same thing happen, right? So this carbon right here had these H's. And again, I'll kind of highlight that one in red for us. Just kind of differentiate it. The carbon on the right-hand side had 3 hydrogens on it, so -1, -1, -1, and it's attached to this carbon, which is a 0. So it looks like it went to -3. So that one went to -3. So both of them went down, or in other words, both of them, this was a reduction. Right? They both went down, they both gained electrons. So this would be a reduction where we added hydrogens. And again, you might remember that, right? You may have learned catalytic hydrogenation is a reduction, or call it a reduction of alkenes, for example. That's what we're talking about, and it is a reduction. Technically, the oxidation states do decrease. Now, if we look over here at the aniline going to nitrobenzene, it's kind of the same story. The one on the left is a little more straightforward. So the nitrogen here is attached to a carbon, and it's attached to 2 hydrogens. Now, hydrogen is less electronegative than nitrogen, so I'm going to give that a -1 for each of those hydrogens, right? There's 2 hydrogens there. And carbon is also less electronegative than nitrogen. So altogether, this nitrogen here will be a -3. It's attached to 3 things that are less electronegative than it. Hydrogen and carbon, all of them are less electronegative. Now, if I look at this nitro, I think I'm going to draw this out so you can see it a little bit more. Nitro groups look like this, right? -1, there's a positive here, and then you have the rest of your benzene ring. Now, this is a good example of one that has a charge because we do need to kind of account for that. Let's see, I'll do this in green just to make it look a little different. So again, we're looking at this nitrogen here, right? So I'm talking about this sucker. I want to know what's the oxidation state of that. And so what you're going to end up doing is you're going to still assign, right? So it's a -1. Let me go back. -1 for that oxygen, -1 for that one, -1 for that one, and a -1 for the carbon down there, right? This is attached to a carbon on that aromatic ring. So it might look like oh, I'm sorry, I keep messing that up. Oxygen is more electronegative than nitrogen, right? So I'm going to give it a +1, a +1, a +1, and it's still a -1 though for the carbon because the carbon is less electronegative. So if you take a look at this, you might be tempted to say that this is a +2, but you have to take into account the positive charge here. Now the positive charge just means, right, that it has lost an electron already. So if you imagine blowing this up, you would have lost 6 electrons from around that nitrogen, right? 2 for each of the bonds to nitrogen, and then you would have gained 2 by that bond to carbon. So your nitrogen, if you took away everything, your nitrogen would only look like this, right? It'd only look like that. So you'd be doing 5 minus 2 is +3. So this oxidation state would be +3. +3. So what we ended up doing, right, was we ended up adding that charge. So, right, so we went +1, +1, +1 for all the oxygens, -1 for the carbon, but then we had to take into account the fact that there's a plus charge, this plus charge right here, right on it. So +1, +1, +1, -1, +1 gives you +3. Or in other words, definitely got oxidized, right? We went from -3 to +3. It was an oxidation. So sorry that turned into a really long video, but you can assign formal charges. They may help you identify if things are oxidation or reduction reactions. Hopefully, though, we're going to not have to do this a whole lot because I want you to watch the next video, which is basically trying to find other rules of thumb to very quickly, without having to figure out oxidation charges, how to very quickly figure out if something's an oxidation or reduction. All right, so please go ahead and practice this. I'll post a worksheet for you all Happy studying. Good luck.